Hello, everyone, and welcome to my lab. Are you ready to learn? Yeah! Are you ready to have some fun? Yeah! Well, let's get started then. Here we go. Can you see that? Let's turn the lights down to see if we can see it better. All right, with the lights down, now you see a blue flame, and if I spray this liquid into it, and I'll spray another liquid into it, and let's do it together. Okay? These are examples of what we call a combustion reaction. This is when something combines with oxygen and burns. Now, the combustion reaction that we have is when natural gas burns, and that is what is happening in this burner. Not everything, not every substance burns. Lots of substances do not burn. And when you came in, and right now you can take a look and you see that we have lots of different pieces of equipment and chemicals on the tabletop, but you also notice that we have some things up in the air. What do we have up in the air? Now, how many balloons are there? What colors are those balloons? And so here's what I hear you saying. There are 6 balloons, and each one of them is red, yellow, and blue. Is that right? No, no. 2 balloons are red, and 2 are yellow, and the remaining 2 blue. Are these big balloons or small balloons? Medium, yeah, medium. Are they about the size of my head? A little bit bigger than that, right? So we always try to make observations and relate these observations to something we already know. There is a combustion reaction going on in that burner, and I'm going to use a different burner right now to ignite, again, natural gas, but you can see that the flames have different colors. What color is this one? And this is an example of what we call a controlled combustion reaction. Nothing is going out of control as long as we are careful. Now, what do you suppose we have in those balloons that are up in the air? Helium. Some are saying helium. You say helium because you know from experience that helium-filled balloons are lighter than air. Other people said hydrogen, and hydrogen is a gas also lighter than air. I will tell you that helium is a gas that does not burn. So one way to find out what's in those balloons is to put the flame to them. All right? So I'm going to come over here and try to reach for this balloon and ignite it. I see that some of you are covering your ears. Why are you covering your ears? Because you know from experience, there's that word again, that there might be some sound energy given off in addition to the light energy that we get from the combustion reaction. So, here we go. Are you ready? That balloon popped. That balloon had in it the gas helium, and helium is a gas that does not burn. As we always do in science, I am now going to repeat the experiment. So I'm going to reach for this other balloon, and did the same thing happen? Yes, and that's what we try to be on the lookout for. All right, so we'll move on to the next balloon, and we'll bring the flame to it, and did that balloon have helium in it? No. That balloon had in it a gas we call hydrogen. And hydrogen combines with oxygen in an uncontrolled combustion reaction. Do you know what another name is for uncontrolled reactions like that? An explosion. An explosion is an uncontrolled combustion reaction. Now, what do we always do in science? We repeat the experiment. So we're going to repeat the experiment, and we're going to do it in the dark. So with the lights down, please. I'll bring the flame to the balloon, and Did you see the ball of fire? Did you see the ball of fire? Did you see it better with the lights on or the lights off? That's something we should remember when we're looking for the release of energy in the form of light. We should do the experiment indoors, not in the sunlight and in a darkened room. What I'd like to ask you to do now is to look at the monitor and watch this very last reaction we did in slow motion. You won't hear any sound. There is the explosion. You see that big ball of fire? All right, now, we have done now 4 balloons, and you are very observant. You must have observed that in addition to sound energy that's being given off, that the loudness of the chemical reaction is getting greater. And before we do the next set of balloons, what I'd like to ask you to do is to protect your ears from potential damage by taking both fingers and you stick them in your ears very tightly. I can't do that and do the experiment at the same time, so I'm going to use earplugs. And I would like to ask you to really protect your ears by sticking both fingers in very tightly. I can't hear you, but I can see you smiling. That means you're hearing my voice. And please protect your ears as we go on to the next balloon. That balloon, I know it's all very exciting, but let me tell you, that balloon had in it a mixture of hydrogen and oxygen. There was a lot more oxygen available for the hydrogen to combine with. And so next what we should do is what we always do in science. What? All right, and let's do that in the dark. So with the lights down, please. And the ears well protected. Here we go. Well, turn both burners off, and let's take a quick look at that last combustion reaction, uncontrolled combustion reaction in slow motion. Again, you won't hear any sound, and there it is, a lot faster than the previous one because there is more oxygen available for the hydrogen to combine with. All right, so what I'm going to do next is a series of experiments with a different substance. Not a gas, but this substance is a solid. And before I touch this solid, I'm going to put my gloves on because this solid is very cold. It's called dry ice. Here is, oh, you know about dry ice, huh? Here is a chunk of dry ice, and its temperature is minus 78 degrees Celsius. You know, in science, we use the metric system. We keep track of the temperature in degrees Celsius, not degrees Fahrenheit. And everyone should be able to convert from degrees Fahrenheit to degrees Celsius. And if you don't know how to do it, then you can ask your teachers, or you can ask your parents, right? Parents, you can help with that too, can't you? Minus 78 degrees is the temperature of this dry ice, which is a solid, and it's changing from being a solid to a gas directly. It does not melt. When a solid changes from being a solid to a gas directly without melting, we call that process sublimation. Sublimation is happening right now, but we can't see it because carbon dioxide gas is invisible. It has no color. And it also has no smell. So we say it is colorless, invisible, and odorless. But sublimation is happening right now. And I'm going to do an experiment with more of the dry ice that I have here using these cylinders that are in front of me. How many cylinders are there in front of me? And are they arranged in some kind of pattern? Do they have a pattern to the arrangement? Can you see? Yes? You can see that 2 cylinders have the same colored liquid in them. Over here, again, another pair over here with the same colored liquid. This is a third pair with the same colored liquid, a fourth pair, and a fifth pair. And what I'm going to do is take chunks of dry ice and drop them into these cylinders in a very special way. And when I get done, you tell me what that special way is. So here we go. You see any bubbles? What kind of bubbles are those? They're gas bubbles. What kind of gas? Carbon dioxide. Where's the carbon dioxide coming from? It's coming from the sublimation of the dry ice. You can also see lots of other interesting things happening, right? Their color changes, and there are beautiful bubbles. And you know, the brain absorbs all kinds of information through the eyes, and through the touch, through the skin, through the nose, through the ears. But the brain can't keep up with all of the information that we're getting. That's why I've organized this experiment in pairs, so you can go back and see what the original color was before the dry ice was put into it. Carbon dioxide gas combines with water to form carbonated water, and that forms carbonic acid. And these different colored liquids have added to them dyes that change color when the pH of the solution changes, when the pH of the liquid changes. pH is a measure of how acidic or basic a substance is. In this case, the carbonic acid is combining with a household ammonia that I put in those cylinders before we got started. Now, you see that there is something coming off the top of the cylinders where I put the dry ice. What does this stuff look like to you? It looks like smoke, but it's not really smoke. It looks like clouds or like fog. You know what clouds and fog are? They are water vapor that has condensed. So we call that condensed water vapor. And the condensation is taking place on the carbon dioxide that's coming from the sublimation process. And you notice that the fog is flowing downward, telling us, if we didn't know it, that carbon dioxide gas is denser or heavier than air. And if we did know it, we can just look at this beautiful display and enjoy it. Now, to do the next experiment, I'm going to get the bucket of dry ice and put it right over here. And I'm going to get an empty dishpan. It's empty except for air. Air is invisible too. And I need one more ingredient, so I'm going to ask for some help. Will someone please bring me out some hot boiling water? Could you do that right now, please? Welcome, Bucky. Thank you very much, Bucky. Thank you. Thank you, Bucky. Good to see you. Happy to see you, Bucky. Yeah. Bucky is a very good science student. Not only is he wearing a Science is Fun button, but I want everyone to notice that Bucky is wearing goggles. Because we all obey, yes, we all obey the safety rules, yes. Now, Bucky, what I'm going to do is take the hot boiling water that you brought me. I'm going to use the same gloves now to protect my hands from heat, not from cold. I'm going to dump this water into the dishpan. And do you see anything coming off the top? Steam is invisible. You can't see steam. What you're seeing is condensed water vapor. And Bucky, what I'd like you to do is to pick up this bucket of dry ice and dump it into this hot boiling water. Whoa! We're still here. This is how they make fog in the movies sometimes. They take hot boiling water and add dry ice to it. And you notice that the fog is moving downward because carbon dioxide gas is denser or heavier than air. So this is a pretty exciting experiment. And Bucky, I want to thank you for helping with this experiment. Bucky, Are you going to graduate on time? How many years is it going to take you to graduate? 1, 2, 3, 4. 4 years. That's good. Wait a minute. I have 5 and you have how many? That's kind of interesting, isn't it? But we all know why, right? So 4 years, and that's what everyone should do. Bucky is setting a good model for every student to graduate in 4 years. Yes. Now, in order to graduate, you have to do well in your coursework, and you have to do well on final exams. I know final exams are coming up now very soon, and you have to go and study, but Bucky, by any chance, can you stay for the rest of this presentation? Do you want Bucky to stay? Can you stay, Bucky? All right. I have a special place reserved for you right over there. I'd like you to go, sit, and enjoy the rest of this presentation. Thank you, Bucky. The next experiment I'm going to do is with another liquid that has carbon dioxide dissolved in it already. This is a carbonated beverage. Everyone knows about carbonated beverages because they have in them carbon dioxide. And so what I'm going to do is open this bottle, and you hear a familiar sound. That's because the carbon dioxide is pressurized. It's dissolved in liquid under a great deal of pressure. And when you open the cap, then you release some of that pressure. And I'm going to take this carbonated beverage, and I'm going to pour some of it into this tall cylinder. What do you see down here? What is that foam? It's carbon dioxide. And carbon dioxide is coming out of the liquid because it's not as pressurized as it was before. You know what happens when you drink a carbonated beverage. What happens? What do? You burp. Yes, you do burp. That's because the carbon dioxide is coming out of the liquid. If you do burp, do it politely and gently, right? So here's an experiment you can do. You can do this experiment at home. All you need is a carbonated beverage, and then I'll put in some raisins. Make sure they're fresh raisins that you put in. And you can see something interesting happen to the raisins. You can also add, if you want to, some small pieces of spaghetti. And if you want, you can add mothballs there too. And then you watch and see what happens. You can see, you can follow a raisin. There's one that's going up, gets to the top, and then it stays at the top for a few seconds, and it comes down again. So this experiment tells us something about the carbonation that is in this carbonated beverage. And it is one of many experiments that we have on the Science is Fun website. I invite you all to visit the Science is Fun website so you can get the directions and the instructions for doing not only this experiment, but other experiments that are exciting and are fun. This experiment had carbon dioxide in it. Now I'm going to do a different experiment over here using these plastic bottles. These two plastic bottles have at the bottom a small amount of a clear and colorless liquid. I will tell you what this liquid is. It's called hydrogen peroxide. In hydrogen peroxide, this is 30% hydrogen peroxide, very concentrated hydrogen peroxide. It decomposes. When it decomposes, it turns into oxygen and water. In science, especially in chemistry, we study what catalysts can do to the rate of a reaction. And I have a powder in this bottle. I'm going to take a small amount of this powder and add it to the hydrogen peroxide to see if it has any effect on the rate of decomposition of the hydrogen peroxide. So I'll take some and simply add it. It looks like a genie came out of the bottle, right? So this powder is called manganese dioxide. It's a solid. It's a solid that catalyzes, that speeds up the rate of decomposition, and we get water vapor. It comes out, and it's hot, so when it hits the atmosphere, then when it hits the air, it condenses. This reaction is one that releases energy in the form of heat, and you can see that something has happened to the size of this bottle compared to what it was before. What has happened? Well, this is a plastic bottle. You've heard of shrink wrapping, haven't you? That's how it works. You take the plastic that you want to wrap something in, and what do you do to it to make it shrink? You heat it. That's what happened over here. So this is a chemical reaction that released energy in the form of heat and caused the plastic bottle to shrink. What do we always do in science? So we're going to repeat the experiment one more time, and I'm going to do it with this other bottle right here. Okay, ready? Here we go. So what came out of the mouth of the bottle? Water vapor. It was hot, and then it condensed when it hit the cold air. And did this bottle shrink? Yes. So that's a very interesting experiment to look at in terms of the release of energy in the form of heat and the presence of a catalyst. Thank you. Thank you. Now what I want to do is take this beaker that has in it a clear and colorless liquid, and I'll tell you that this liquid is a mixture of a solution of something we call potassium tartarate and also hydrogen peroxide. They have been mixed together and heated to a temperature. Let me read. I have a temperature measuring device here. It's about 72 degrees. And a chemical reaction takes place between the hydrogen peroxide and the potassium tartarate, but it doesn't seem to be going. So what we have to do to speed up the rate of a reaction is add a catalyst. I have a catalyst now in the form of a liquid. This liquid is a solution of a metal ion called cobalt. It's actually a solution of cobalt chloride. One of the characteristics of a catalyst is that it is not consumed in the chemical reaction. It is used, but then it's regenerated. So I want you to remember what the color of the catalyst is as I take this catalyst and add it to the mixture of hydrogen peroxide and potassium tartarate. You can see the bubbling. That's carbon dioxide coming from the oxidation reduction reaction. And now you know why I have a tray here. But what I want you to take a good look at is the color of the liquid, and the catalyst has been regenerated. Right? In my lab, we have a lot of excitement, and I know all of you are excited about the experiments that we are doing and the other experiments we're going to do, but you really never can guess who else might stop by in my lab.
Ho, ho, ho! Ho, ho!
Oh, it's Santa Claus.
Oh, Merry Christmas! Merry Christmas! Merry Christmas! Oh, ho, ho, ho! Ho, ho, ho! Ho, 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 ho! Ho, 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 ho! Bucky!
Hello, Santa.
Hello, Bassam!
And welcome to my lab.
Why, thank you.
Thank you for taking time out in your this is the busiest time of the year for you, right?
Very busiest time of the year.
I really appreciate your being here, Santa. Did you get my list, Santa?
I got your list. Yes, you had 4 items.
Oh, my goodness. Did I get any of them? I think I've been good. Have I been good?
Been good? Oh. You were on my good list.
Well, I'm glad to hear that.
Okay.
Let me see what...
I've got a very special book for you, Uncle Tungsten.
Uncle Tungsten.
But
this
it's more special than that because if you open and look, it's inscribed to you.
Oh, this is an outstanding book. It's written by the famous physician and author Oliver Sacks, and it is his memories of his own childhood and how he got inspired by his uncle who ran a tungsten factory. You know, tungsten is used as a filament in light bulbs. And when Dr. Sacks was growing up, I had a chance to look at this manuscript before the book came out, and I really, really recommend it to everyone. You know, tungsten is one of many elements that we have in the periodic table. The periodic table consists of a whole bunch of elements. Most of the elements are metallic, and tungsten is one of those elements. Thank you, Santa, for being so thoughtful to arrange for me to get this.
I'm very pleased that you like it.
Thank you.
You ready for your next one?
Yes, I'm ready for the next one.
Okay. Well, you were talking about the periodic table and the element. I brought you an element clock.
Oh, my goodness. Look at that. The numbers have been replaced by the symbols of those elements: hydrogen, helium. You can read. Can you tell time by this? Yes, of course you can tell time by this. It's very, very nice. Thank you very much, Santa. I really appreciate your getting this for me.
You asked for some special lights for the tree?
I wanted those special lights. These are new lights.
These are new.
These are, yes, I wanted LED lights. LED.
LED. That stands for light emitting diode.
Santa knows a lot of science, doesn't he, right? Yes, that's very good, Santa. And is there something special about light-emitting diodes? Yes?
Yes, compared to a light with a filament, they might make much more light for the same amount of electricity. They don't run hot.
They don't get heated up. That's very, very interesting. So,
yes, turn it on.
Yes, they can turn it on, and they use elements from the periodic table, especially ones that are semiconductors. Thank you, Santa.
One more gift.
One more gift. Let's see if I got what I wanted.
I bought you these sticks.
Oh, you got me the light sticks.
Yes.
Yes. Very, very interesting. Let's show everyone what these light sticks do.
Right.
Let's do it with the lights down, all right? Let's do it with the lights down, and you're ready? Here we go. We bend them, and we get the release of energy in the form of light, but now heat here. They're the same temperature. These are kind of interesting to play with, right?
Yeah.
Right? This is all friendly here. Yeah, we're friends. Thank you, Santa.
My pleasure.
And this of course is called, what do you call it in your workshop?
Chemiluminescence.
That's what we call it too. Chemiluminescence. This is the release of energy in the form of light, but no heat is being released. And Santa, with your permission, I'd like to do a chemiluminescent experiment.
An experiment
that we've been working on here. Would you be willing to help?
You want me to do an experiment?
Yes, I'd like
you
to
very
help.
willing to,
yes.
But I need...
Oh, Santa needs goggles, and I have goggles for Santa right here.
Thank you.
There we go. There we go. Santa is well prepared, and I am too. So what Santa is going to do is take this clear and colored liquid.
Yes.
Now I'm going to take this clear and colorless liquid. We're going to mix them in this funnel that's connected to a glass spiral assembly. And we're going to do this in the dark. So with the lights down, please. When you're ready, Santa, I am ready.
All right. Ooh, the sound, that is beautiful.
I'm glad you like that, Santa. That's another example of chemiluminescence. Santa, I know this is the busiest time of year for you. You're probably double parked out there. The reindeer are probably eager to go.
That's true.
I want you to give my best to Mrs. Claus and all the elves, and I wish you the happiest of holidays. Thank you so much for coming, Santa. Thank you for coming. Thank you very much. Thank you, Santa. Thank you.
Yes.
Thank you very much.
Goodbye.
The next experiment I'm going to do is one where I'm going to take a match and light a candle. Actually, I'm going to light 2 candles. And some of you are thinking, well, did we come all the way to see Professor Shakhashiri light a candle? This is something that happens all the time. But I want to do some experiments with those candles. So I'm going to reach into my back pocket, and I'm going to get my wallet out. What do people usually keep in their wallets? Money. What else? Credit cards, if you have them, yes. What else? Pictures, yes. What else? Driver's license, if you're old enough to drive and you've qualified, right? So I'm going to reach in, and I'm going to take a dollar bill out of my wallet, and I'm going to put this dollar bill right here in the flame, and you can see it's all gone. Was that too fast? Did that happen too quickly? That's why I want you to pay close attention, because what I used was not a real dollar bill. It was a fake dollar bill. It was a phony dollar bill. And I'm going to do what we always do in science, repeat the experiment. This dollar bill is made of paper that has been treated with chemicals so that when it burns, it doesn't leave any ash behind. So let's do it now. I bring it close to the flame, and as soon as it touches the flame, there it is, disappears into thin air. All right. What I'm going to do next is go again into my wallet and get a real $20 bill now. No. Well, in my lab we do lots of fun things, but we do them obeying the safety rules. So what I'm going to do is take this jar that has in it a clear and colorless liquid. What does it look like? Water. Looks like water. Again, you say water from experience. This liquid, we describe it as being a clear and colorless liquid, as is water. And what I'm going to do is take the $20 bill, and I'm going to soak the $20 bill in this clear and colorless liquid, and then I'm going to fish it out, and you see it's dripping like any wet object would. And now I'm going to bring it to the flame, and there you see the $20 bill on fire. Or not? You did see a flame, right? That flame, you did see a flame, but the $20 bill is intact. Now, I asked you, can this liquid be water? This liquid is a mixture of something we call rubbing alcohol and water. It's an equal mixture of the two. It's half and half. We learned from this experiment that the alcohol burns at a lower temperature than the temperature at which the paper from which this $20 bill is made burns. And the water cools down the flame so the paper doesn't catch on fire. This is a good $20 bill. I'm going to put it back in my wallet and use it a little later. I'm going to do an experiment now with another element in the periodic table which is not metallic. This is the element sulfur. And to do that, I need to reignite this burner, because what I want to do is burn solid sulfur. And I'm going to burn the sulfur, and when sulfur burns, it forms sulfur dioxide. And this will happen by my taking this cork off. It has a spoon at the bottom. I'm going to fill this spoon with the sulfur, just like that. And then I'm going to stick the sulfur in the flame, and the sulfur melts and begins to burn. If you turn the lights down, please, you'll begin to see a flame coming from the combustion of the sulfur. And it's a luminescent flame, of course, very pretty blue. But if I put it back in this, if I put it into this flask, it has oxygen in it. you can see this beautiful glow, and it is happening this way because we have more oxygen. A lot more oxygen, and with the lights up, what happened is that the smoke kicked the cork out. So this was a sealed, and I should have released the pressure a little bit, but everything is okay, and everybody is doing very well. All right, now I turned the burner off here, and I'd like to ask you to focus your attention on this large beaker that I have here. This beaker, I want everybody to look at this beaker right now. This beaker has a volume of 4 liters. If you look at the beaker right now, you just learned how big 4 liters is, and you cannot unlearn it. You may forget it. That's different. That's how the brain works, yes. So I have this beaker. It's empty except for air. I'm going to take a magnet that's coated with Teflon and put it right there, and then I'm going to push the button to have the light from below. Come on, push the button. Yeah, there it is. Yeah, and I'm going to turn the motor so that the magnet spins. And it spins and making some noise, but not too much noise. Can you see the magnet spin? Yeah, all right. So what I'm going to do now is mix different liquids in this large 4-liter beaker. The first one is a clear and colorless liquid, although now you can see it's not as clear. It's somewhat cloudy. And the next liquid is clear and colorless. I add that. Anything interesting happen so far? Well, the volume increased. That's not terribly interesting. It's relevant, but not very interesting. I add the third liquid, and you see that there is a change. Can you see what's going on? I can't see anything happening. I can't see anything happening. How come I can't see anything? Oh, you're not paying attention to me anymore, are you? I can't see anything happening. How come I can't see anything happening? I'm not looking. What's the big deal about looking? The last time I looked, the color of the liquid in the beaker was blue. So every time I look at it, it's blue. You tell me when to look, all right? You help me out. Tell me when to look. Right now, right this second. I don't want to trip over anything here. So I look right now. See, it's blue. Every time I look at it, it's blue. You help me out. Tell me when to look. Right now, you sure? Right this second? Yes or no? Yes or no? See, it's blue. Ah, maybe you on this side can help me better, right? Tell me. Should I look at it right now? Now? Right now. Right this second. You sure? Right now? See? It's blue. Every time I look at it, it's blue. What is it that you were doing that I wasn't doing? Now, you're right. You were looking at it all the time, and I wasn't. And that's something we should remember when we do experiments. When we do anything in life worth doing, we should be involved in it. Not just mix things and then look someplace else, because if we do, we miss out on a lot of interesting changes, including these beautiful color changes in this chemical oscillating reaction, which has in it about 8 or 9 different chemicals. It's got water, malonic acid, potassium iodide, hydrogen peroxide, manganese sulfate, sulfuric acid, even potato starch is in there. And this yellow color that we see is the color of iodine. And the iodine combines with the potato starch and gives us this deep blue color. That's characteristic of iodine combining with potato starch. This chemical oscillating reaction is a fascinating reaction. We do research to try to understand what it is that causes this beautiful, captivating behavior to take place. So I wanted to share that with you because it really is a very interesting system. At this time, I'd like to do an experiment using a metal that everyone knows about. It's called copper. I have a piece of copper in the shape that you see right in front of me. What I'm going to do, you see it is shiny, and what I'm going to do is heat it. I'm going to use a burner to heat it, so I'm going to turn the gas on, and there, get the burner going. I want this to be real hot because what we're going to look for is any changes that might occur. We make observations to see what might happen as, in this case, we are heating this piece of shiny copper. Copper is a very common metal, but when it is heated, you're beginning to see some changes. Can you see any changes? The copper surface is getting darker, and there's a green flame, part of the flame that you can see. What is happening is the hot copper surface is combining with oxygen from the air and forming a deposit of copper oxide. So copper oxide is a lot duller in appearance than the shiny copper surface. You can see that now. What I'm going to do next is turn off the flame completely, and I'm going to add some hydrogen gas to this copper from this cylinder that's hooked up to this funnel. So I'm going to turn the gas on, and you can hear it flowing. I'm going to bathe this hot piece of copper with hydrogen gas. Hydrogen gas combines with the copper oxide to form water and copper. I take the hydrogen away, I get copper oxide. Put the hydrogen back in, and I get copper. And of course, we do this experiment and close off the hydrogen valve quickly because we don't want any hydrogen to be in contact with a flame or any other source of ignition. You remember what happens when hydrogen combines with oxygen. We get what? An explosion. So, all right. Now to do the next set of experiments, I'd like to ask you to welcome another person who's been in my lab for a long time, and that's Elizabeth. Please welcome Elizabeth. Hi, Elizabeth.
Hi.
What do you got there?
Well, first of all, I have a strong magnet.
This is a strong magnet. How can you tell it's a strong magnet?
Well, we can test it out on something.
Let me see. I might have my pocket knife here. Let me just check out here. Yes, I do. Here's, yes, it is indeed a strong magnet. All right. What else you got there?
Well, I have a tube here.
You've got a tube, yes,
Yeah.
and
Let's see if that's attracted to the magnet.
oh, you want to find out if it's magnetic or not. So I put the magnet, then it, no, I have to keep holding it. So it's not magnetic. What
Right.
kind of a tube is this?
That's a plastic tube.
Plastic tube. What about this tube here?
This one's a copper tube.
Copper, just like the one I was working with. Let's see. Do you think copper is going to be magnetic or what? How do we find out? We try it. We do the experiment. So I put the magnet here. It doesn't stick to it. So copper is not magnetic. All right? So what shall we do next?
Well, if we could go over here.
Get over here? Certainly. Oh, you want to get up on the platform?
Yeah.
All right. May I help you?
Yes, thank you.
All right. What would you like next?
The plastic tube and the magnet, please.
A plastic tube and the magnet. I'll put the copper tube on the side over here. And what are you going to do now?
Okay, I'm going to drop the magnet through the plastic tube, and if you could catch it.
All right. Let me catch it in this plastic tub that I have over
Okay.
here. All right. So I'm ready to catch it when you're ready.
Okay. Is everyone ready? Yeah. 3, 2, 1.
Whoa. That came down fairly quickly, and I heard it, right? All right. What shall we do now?
Let's try it with the copper tube now.
With the copper tube. So here's the copper tube. I put the plastic tube over here. And I'm ready.
Okay. 3, 2, 1.
Wait a minute. Did you see what I saw? It came down, the magnet came down slower, right? Want to do that again?
Sure.
All right. Here we go. Let's
Okay.
watch.
3, 2, 1.
A lot slower. A lot slower. That's very interesting, Elizabeth. Perhaps you can explain that when you step down here. Let me just keep this copper tube away from you. Yes?
Thank you.
So what was happening in here?
Well, when the magnet passes through the copper tube, it generates an electric current, which magnetizes the inside of the copper tube and slows down the magnet.
Very interesting. That's a very good explanation. Thank you very much, Elizabeth. Thank you. I know you've been working with other metals, and do you have any of them around here?
Actually, I do. Here I have 2 steel balls.
All right.
You could take one, I'll take the other.
All right, I'll take a small steel ball. That's right here, right? Those 2 small balls. Yeah, what shall we do with them?
Well, first we're going to try dropping them on the table.
Okay, so you want me to count?
Yes.
3, 2, 1. They're not very bouncy.
Let's try that again.
All right, 3, 2, 1. They're still not very
It
bouncy.
doesn't work.
Yeah.
Well, over here, I have 2
You have
other metals.
Oh, you have other metals.
Right.
All right.
One of these is a crystalline metal, which is very soft for metal. And the other is an amorphous metal, which is very hard. And now we're going to try and bounce the steel balls off of these metals.
All right, I got my ball right here.
Okay, we need these plastic tubes.
Oh, put the plastic
Cover.
tubes on top like this.
Right.
Okay. Now what?
Okay, now we just drop.
Oh, we do another count again? Okay. 3, 2, 1. Hey, yours is a lot livelier than mine. Yours is still bouncing. Mine is stopped bouncing. Why is that, Elizabeth?
That's because the amorphous metal is so hard that it doesn't absorb the energy from the ball as quickly.
Very interesting. Very interesting. Well, thank you for showing us this very interesting experiment. What I would like to do next is say that all metals are found in nature, either in the free state or in combination with other elements. And we find minerals all over the place. And I have some rocks, very interesting rocks, that I'd like to show you here.
Okay.
May I? So let me get my tray of rocks and put the tray right here. These are really interesting rocks. Excuse me for taking this out of the way.
They don't look very interesting to me.
But they are very interesting when we look at them using a source of ultraviolet light, which is what I have down here. I have 2 sources, one for you and one for me. Mine is a long wave UV lamp, what we call a black light, and yours is a short wave UV lamp. So let me turn the switch on here, and if we may have the lights down, please, then let me pass the long wave UV lamp, and now you can see why I say the rocks are really interesting, because they're exhibiting a phenomenon we call fluorescence. And this is one way of finding out the identity of the various minerals that we have. So this is with long wave UV. Yours is short wave UV, and let's try yours now.
Okay.
Very pretty. Very pretty. And by using fluorescence methods, we can identify the different minerals and then extract the metals from them and use them for a variety of different purposes. So let's have the lights back on, please. And I'd like to show you another experiment using a black light.
Okay.
To do that, I'm going to have to put some gloves on. So I'll do that quickly, because the next thing I'm going to do is put some Vaseline on my hands. And you know what that does? It makes them all very sticky. So I'm going to take a big glob of Vaseline like this, all right? I'm going to rub it in like so. Do you see anything different about my gloves? Yeah, they do, yeah. But I want you to now look at my gloves with the lights down using the long wave ultraviolet lamp, the black light. So could you do that?
Okay.
Just get that can out of the way right there, yeah? Just put it on the side. And now, can you see my gloves now? And I put some on the tabletop here, so that's glowing too. Now with the lights back up, you can see there is no fluorescence whatsoever here. Only when you use black light, you can see this effect. So it's not only in rocks, but in other chemicals. And fluorescence is a very common method for analyzing a variety of substances. Thank you very much, Elizabeth.
Thank you.
Thank you. The next experiment we're going to do involves a gas and a volatile liquid. And this experiment is going to be done by using a match that I'm going to strike first and then drop into a long glass tube that has in it the mixture of the gas we call nitric oxide, and the volatile liquid is called carbon disulfide. And I'm going to try to do that where the tube is, of course. I can't do it anywhere else. This tube, see, long glass tube, it's got a rubber stopper at the bottom, rubber stopper at the top. I'm going to step on this stool. I'm going to take a match and strike the match. Bring the match close to the mouth of the tube with the lights down. Take the stopper off and I'd like you to take a look at this in slow motion now. Won't hear any sound. You'll see me drop the match. I'm trying to get it out of the way right there. You see that? And I'd like you to take a look at the tube now. It's full of sulfur. The nitric oxide is combined with the carbon disulfide. It released energy in the form of light. That's another form of chemiluminescence. And of course, we have a deposit of sulfur inside the glass tube. All right, now we'll do this experiment in a flask that has a clear and colorless liquid at the bottom. And I also have another clear and colorless liquid that I'm going to mix in this big flask with what's in it already. And you know that a chemical reaction takes place when you see color changes. You can see that we have a dark liquid now. We started out with clear and colorless liquids. But for a chemical reaction to take place, we have to mix the chemicals very, very well. Can you see anything different now about this flask than before? I can see myself in this flask right now. What we've done here is prepare a silver mirror. There's a thin deposit of metallic silver that came out of the mixture that I used. In fact, this is how they used to make mirrors, and this is how they make holiday ornaments. So during the holiday season, if you go around town and see big ornaments like this, you know where they were made. I want to thank you for coming to this special presentation, and I want to really remind you that no matter what you do, science is fun. Thank you very much. Thank you. Thank you very much. Thank you. Thank you. Thank you.
For dancing raisins and other fun experiments you can do at home, check out the Science is Fun website at www.scifun.org. You'll discover more fascinating facts about chemicals and other great science information.